Hello student, in this lecture I will discuss about if we add one more zero or one more pole in transfer function, then what will happen. Okay, so first we consider the case effect of adding a zero to a system. Okay, so let's start our discussion. So what actually we will discuss, if we add one more zero in our transfer function, then what will happen. Okay, so see, let us consider a second order system with transfer function of this. That means Cs by Rs is equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square. Now let us introduce a 0 at s equal to minus z to the above second order closed loop system. Okay, so if we add 0 at s equal to minus z in this equation, then we get Czs, that is our new transfer function after adding a 0 at s equal to minus z. So our new transfer function is Czs divided by Rs is equal to s plus z into omega n square divided by s square plus 2 zeta omega ns plus omega n square. Adding a 0, see, adding a 0 to the transfer function affects the DC gain of the system. Now what is the DC gain? So see, when a stable control system is excited with a step input, the response attains a constant level at steady state. Okay, the term DC gain is defined as the amplitude ratio between the steady state response and the step input. Okay, so this is our DC gain. So adding a 0 to the transfer function affects the DC gain of the system. Okay, so because in first equation, that means in equation number 2.150, the DC gain is 1. Okay, but after adding 0, here the DC gain is not 1. Okay, so therefore to make the DC gain unaffected, that means to bring the gain to unity, divide the numerator by z. Okay, so if we divide the numerator of equation number 2.151 by z, then we get Czs by Rs is equal to s plus z into omega n square divided by z, and this whole divided by s square plus 2 zeta omega ns plus omega n square. Okay, so here the DC gain is, in this equation the DC gain is 1. Okay, so why we divide the numerator by z? Because to bring the DC gain to unity, we divide the numerator of the new transfer function divided by z. Okay, now to analyze the effect of adding a 0 to the system, we have to find the time domain specification. Okay, now see, we can write equation 2.152 as equation 2.152. See, we can write the equation 2.152 as like this: Cs by Rs is equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square plus s by z, and this whole into omega n square s square plus 2 zeta omega ns plus omega n square. Okay, and I give this equation is 2.153. So I give the equation number of this equation is 2.153. Let Ct is the step response of the system omega n square divided by s square plus 2 zeta omega ns plus omega n square. Then the step response of s by z into omega n square divided by s square plus 2 zeta omega ns plus omega n square is 1 by z d dt of ct. Okay. Now, therefore, the step response of the system with added 0 is Czt equal to Ct plus 1 by z d dt Ct. Okay. So, now the equation number 2.153, we can write this equation 2.153 in this manner: Czt equal to Ct plus 1 by z d dt Ct, and I give this equation is 2.154. Okay. Now see the response of the system with added 0 Czt and the response of the original system is Ct are shown in this figure. So after adding 0, the response is Czt. Okay, and the response of original system, that means our general second order transfer function response is Ct, which I have shown the characteristics of this equation, of these two equations in this figure. Okay. So from the response we can observe the following. First one is the rise time of Czt. Czt means after adding 0 of our first equation, that means general second order equation. So first observation is the rise time of Czt is less than that of Ct. Hence the peak occurs in Czs earlier than Cs. Okay. And second one is the maximum peak overshoot of Czt is greater than that of Ct. So second observation is the maximum peak overshoot of Czt is greater than that of Ct. Okay. So in summary, we can say the addition of a 0 to a system decreases rise time and increases the maximum peak overshoot. Moreover, the values of rise time and peak overshoot depend on the selection of value of z. Okay. Now see, from the equation number 2.153, so see the equation number 2.153. So from this equation we can see the smaller values of 0, that means the 0 close to origin produces large overshoot, whereas the large value of 0, that means the 0 away from the origin produces negligible effect on transient response. That means if we add 0 away from the origin, then this produces negligible effect on transient response. Here Czt, here see the response. Okay, so here see the response Czt and Ct. Okay, so in this case we add 0 away from the origin, so it produces negligible effect on transient response. But in this case we add 0 close to the origin, that's why it produces large overshoot. Okay, so it have effect on transient response. If we add 0 close to the origin, then it produce large effect on transient response. But if we add 0 away from the origin, then it produce negligible effect on transient response. Okay, therefore we can say selecting the 0 near the origin will avoid large overshoot. Okay, now come to the next effect, that is effect of adding a pole. Okay, so see, let us consider a general type 0 system. Okay, so we have considered here a general type 0 system. The general type 0 system GS equal to K into TZ1S plus 1 into TZ2S plus 1 like this, and this divided by TP1S plus 1, TP2S plus 1 like this. Okay. Now see, the steady state error of the closed loop system for a unity step input is ESS, because steady state error we always represent steady state error by this symbol ESS. So ESS equal to steady state error, ESS equal to limit S tends to 0 SRS divided by 1 plus GS. Okay. Now here we consider the step input, that's why RS equal to 1 by S. So here put RS equal to 1 by S. So after putting RS equal to 1 by S, our steady state error ESS equal to 1 by 1 plus K, and this is a constant. Okay. Now see, the steady state error of the type 0 system is 1 by 1 plus K, where K is the steady state gain of the system. An addition of pole at origin in the forward path increases the type number by 1. Okay, so see, an addition of pole at origin in the forward path increases the type number by 1. Therefore, the steady state error of the system for a unit step input after addition of a pole at origin is ESST equal to, that means this equation. See this equation. So see, the steady state error of the system for a unit step input after addition of a pole at origin is this. Okay, so we calculate the steady state error after adding a pole at origin is ESST equal to limit S tends to 0 S into 1 by S divided by 1 plus limit S tends to 0 GS by S. Okay, so after simplifying this equation, we get steady state error is equal to 0 after addition of pole at origin. Okay, so see, we can say from this observation, addition of a pole at the origin reduces the steady state error to 0. On the other hand, if a pole is added other than at origin, then the order of the system is increased by 1. If a pole is added at origin, then type number is increased by 1. Okay. So if the addition of a pole is very close to the imaginary axis, then the system becomes oscillatory. On the other hand, if the added pole is far away from the imaginary axis, then the system becomes sluggish. Okay. Now see, here I have discussed the effect of adding of pole and the effect of adding of 0. Okay. So see, adding some zeros and poles to the original system to improve its dynamic performance is known as compensation. So in next lecture, I will discuss some of the compensation scheme of our control system. Okay, thank you.